Well, welcome back to chapter 13. Just trying to break it up to make some smaller sections, smaller recordings. So we were getting into a variety of elements here, some material. So let me go and get back into the corresponding section that we're focusing on now. Just a second. So the next thing we want to be talking about is prototype development as a risk mitigation technique. So the principles and techniques to identify, manage, and ultimately mitigate risk can be enhanced through the use of prototypes. Significant problem areas may have been identified at this point, and individual strategies are in full implementation by the advanced development stage. However, in the development of a new complex system, the decisions as to which components and subsystems require further development and testing prior to full-scale engineering and issues regarding their physical implementations are frequently more difficult and critical than those regarding their functional design and performance. One of the reasons is that many physical characteristics do not easily lend themselves to analysis or simulation, but rather require the components to be designed, built, and tested to reveal potential problems. So the material we're going to talk about in this section will describe general approaches to identifying and resolving problems in areas that do not lend themselves to mitigation through these methods. During early risk management activities, a system engineering approach to the identification of potential problems areas is to take a skeptical attitude, especially to design proposals unsupported by relevant precedent or hard system engineering data. The system engineers ask, one, what things could go wrong? Two, how will they first manifest themselves? And three, what could then be done to make them right? So what are some of the potential problem areas? In looking for potential problems, it is essential to examine the entire system lifecycle, engineering, prototypes, storage, operational use, and operational maintenance. Special attention must be devoted to manufacturing processes, that is the ILITs, which are reliability, availability, and maintainability, logistics support, and the operational environment. The approach is that of risk assessment. What risk may be involved in each phase? Where are the unknowns, such as the areas in which the prior experience is not sufficient? For each potential risk, the likelihood and impact of a failure in that area must be determined. As in the case of functional characteristics, the most likely areas where proposed components implementations may be significantly different from previous experience can be classified into four categories. One, components requiring unusually stringent physical performance, such as reliability, endurance, safety, or extremely tight manufacturing tolerances. Two, components utilizing new materials or new manufacturing methods. Three, components subjected to extreme or ill-defined environmental conditions. And four, component applications involving unusual or complex interfaces. So we can be talking about examples of each one of those. So first, unusually high performance. So most new systems are designed to provide performance well in excess of that of the predecessors. When such systems are at the same time more complex and also demand greater reliability and operational life, it is almost always necessary to verify the validity of the design approach experimentally. Radars used in air traffic control systems are examples of complex devices requiring extremely high reliability. These radars are frequently unmanned and must operate without interruption for weeks between maintenance periods. The combination of performance, complexity, and reliability requires special attention to detailed design and extensive validation testing. All key components of the radar require development and testing prior to full-scale engineering. Modern aircraft are another example of systems requiring to perform under high stress, which may vary under high stress with very high reliability. Many aircraft have operating lifetimes of 30 to 40 years with only limited renewal of more highly stressed structural and power components. Development and testing of aircraft components is notably excessive. Components used in manned spaceflight must be designed with special consideration of safety as well as reliability. The launch and re-entry environments places enormous stresses on the parts of the space vehicle and on the crew. Special procedures are employed to conceive of all possible accidents that might occur and ensure that the causes of such eventualities are eliminated or otherwise dealt with, for example, by extensive design redundancy. More familiar systems do not have quite such dramatic requirements, but may require remarkable performance. The engines of some of today's automobiles do not require maintenance until 50,000 or 100,000 miles. Such reliability performance has required years of development and testing to achieve those goals. Well, let's explore some examples of special materials and processes. Advances in technology and new processes and manufacturing techniques continue to produce new materials with remarkable properties. In many instances, it is these new materials and processes that have made possible the advances in component performance, as discussed previously before we got into this area. So in the table that we're showing, it lists some examples of the many specialized materials developed in recent years that have made a major impact on the performance of the components in which they are used. In each new application, however, these components have undergone extensive testing to validate their intended function and freedom from unwanted side effects. Titanium has proven extremely effective in many applications, but has been found to be more difficult to machine than steel or aluminum that it replaced. There are other types of metals that can be formed easily into complex forms, but do not have the strength of the conventional formed metal. Some of the new adhesives are remarkably strong, but do not retain their strength at elevated temperatures. These examples show that the use of special materials and critical elements of the components needs to be carefully examined and in most cases tested in a realistic environment before acceptance. So let's explore some of these stressors that may be part of what would cause us to be wanting to use these kind of materials. And so first of all, extreme environmental conditions. The proper operation of every system component depends on its ability to satisfactorily operate within its environment, including such transport, storage, and other conditions as may be encountered through its life cycle. So those would be the kind of things that could come up, things with shock, vibration, extreme temperatures, humidity, special instances of radiation, vacuum, corrosive fluids, and the list goes on and on. So that would be something that we would want to be aware of and consider. Something else to consider is component interfaces. And so I'm not going to go through as much detail this. You can be looking over the textbook, but I'll just give you some broad brushes of these concepts. So component interfaces. And perhaps the most neglected aspect of system design is component interfaces, since these are seldom identified as critical elements, and since they fall between the domains of individual design specialists, often only system engineering feels responsible for their adequacy. So that's something that may fall into the consideration that things need to be considered, and some materials may actually be things that would be something you want to consider in that area. What about component design? So we talked about previously a number of criteria that may be used to identify components that require the development effort to bring their design to a level of maturity sufficient to qualify for them for full-scale engineering. So thus component design would be something that would fall into that we would want to make sure that we adequately cover. Next, we can think about concurrent engineering. There can be a lot of different things that need to be going on in parallel, and to minimize the risk inherent in a variety of circumstances, it has been recognized that the specialized engineers who are particularly versed in production, maintenance, logistics, safety, and other items considerations should be brought into the advanced development process to inject their experience into the decision on design and early validation. So thus we can be getting into this term, concurrent engineering, and the integrated product teams can be having a variety of different people that are supporting that overall effort. For software components should be addressed similarly. Each component is assessed for complexity, and a risk strategy is developed and implemented. Particularly complex components, especially those controlling systems hardware elements, may necessitate the design and testing of many system software components in prototype form during the phase of an effort. Computer-aided software engineering can be something that would be of use to be thinking in terms of how we're going to be dealing with and making sure that software components are functioning properly. What about design testing? So the process of component design is iterative. And so that would be something that we will want to be thinking about, how we're going to be doing the design to validate the functionality of various types of components. Rapid prototyping can be another thing that would be under consideration. And so it is meant to describe the process of an expedited design and build of a test module of a component, a subsystem, or sometimes a total system, to try and see how it all works. And you can like kick the tires, if you will. And so when engaged in rapid prototyping, the term rapid means that adherence to strict quality standards, normally a full part of the system development, is suspended. So you're trying to get a quick look by seeing an actual test article that you could be getting a chance to be exploring and thinking about where you are with the components at that level. Lastly, we can be thinking about development facilities. Sometimes the type of experiments or testing that is done requires some very specialized types of facilities that can have a huge cost to try and stand one up. And so these may be facilities that one has to go and rent, or it's a government facility that you're actually utilizing to make that happen. And so that should be something that should be considered and played into how the testing and assessment are going to be done. And as we're focusing on advanced development, there may be some key things that need to be done that may be subjected to the resources that are available in those kind of locations. Okay, I jumped over some more detailed stuff that's in the textbook for that portion of this section. So refer to the textbook for more details. Next, we'll talk about development testing. The determination that all of the design issues identified during the advanced development phase have been satisfactorily resolved requires a systematic program of analysis, simulation, and test of not only the particular components and subsystems directly involved, but also of their interfaces and interactions with other parts of the system. It also requires explicit consideration of the operational environment, its effect on its effect on system performance. Development testing should not be confused with what is traditionally referred to as developmental test and operational test. Developmental testing typically involves the engineered system within a series of test environments under controlled scenarios. This type of testing is conducted by the developer. Operational testing is also on the engineered system, but involves a customer and is conducted under more realistic operational conditions, including environments and scenarios. Development testing, on the other hand, is on subsystems and components and is conducted by the developer. A well-planned development test program generally requires the following: development of a test plan, development or acquisition of test equipment and specialized test facilities, conduct of demonstration and validation and test, analysis and evaluation of test results, and correction of design deficiencies. In terms of test and test analysis plans, an essential but sometimes insufficient emphasis step is the advanced development process is the development of a well-designed test plan for determining whether or not the system design is sufficiently mature to proceed to the engineering design phase. For the test planning methodology, the overall testing approach must be designed to uncover potential design deficiencies and acquire sufficient testing data to identify sources of these deficiencies and provide a sound basis for their elimination. This is very different from the approach that presupposes success and performs a minimal test with scanty data acquisition. Whereas the latter costs less, initially its inadequacies often cause design faults to be overlooked that later result in program interruptions, delays, and far greater ultimate cost. So in terms of a checklist, we can be thinking of a few things. One, determine the objective of the test program. That would be important. The primary purpose, of course, is to test the subsystems and system against a selected set of operational and performance requirements. And so that would be something we want to do. To review the operational and top level requirements, determine what features and parameters must be evaluated. Key performance parameters identified early in the development process must be included in this test. 3, determine the conditions under which these conditions will be tested. 4, review the process leading to the selection of components requiring development and the design issues involved in the selection. 5, review the development test results and the degree of resolution of design issues. 6, identify all interfaces and interactions between the selected components and other parts of the system. And 7, on the basis of above, to define the appropriate test configuration that will provide the proper system context for testing. 8, identify the test inputs necessary to simulate the components and the output that measures systems response. 9, define requirements for test equipment and facilities. 10, determine the cost and manpower. 11, develop test schedules for preparation, conduct, and analysis of the test. 12, prepare detailed test plans. And so there's a lot of things that need to be in consideration when we're looking at the development tests. Well, let's continue on and think about the test and the evaluation process. One note I'll make, and there's a good discussion about this in the textbook, is consideration of model-based system engineering, model-based MBSE, within the test and evaluation phase may improve testing procedures, shorten the time between design iterations, and assist in the communication within the team. And so the whole idea of model-based system engineering, including what you can be doing with SysML, is something we'll also be doing in our course, mostly with our project work. And so there's a lot of good material that's talked about in this portion of the chapter, but I'm going to skip over it due to time. Let's take a little bit of a thought about the test prioritization. The test planning process is often conducted under considerable stress because of time and cost constraints. These restrictions call for a strict prioritization of test schedule and test equipment to allocate the availability time and resources in the most effective manner. It's always a judgment call, and so having subject matter experts to help is important, but how do you test, especially when the operational environment is very different from what you have access to for doing your development test? And so the choice of specific test configurations in each case requires a complex balancing of risk, cost, and contingency plan, requiring the highest level of system engineering judgment. And so there's more details in the text for that. For the test analysis planning, the planning of how the test results are to be analyzed is just as important as how the test will be conducted. So here are some things to be thinking about for what should be done. One, determine what data must be collected. Two, consider the methods by which these data can be obtained. Three, define how all data will be processed, analyzed, and presented. And so those are some things that you want to make sure that are addressed. Well, we've mentioned a couple master plans, a system engineering master plan, the SEMP. Well, now there's something called the TEMP, the Test and Evaluation Master Plan. And so it can be a formal requirement, say if this is a government-related type of effort that you're doing. So the TEMP is a plan to first to be prepared as part of a concept definition and expanded and detailed at each phase of the development. So the TEMP is not so much a test plan, which also has to be developed, but a test management plan. Thus, it does not spell out how the system is to be evaluated or the procedures to be used, but it is directed to what is planned to be done and when. And so the textbook goes into the specific things that need to be in a TEMP. And so there's a system introduction, having the mission description, operational requirements, measurements of effectiveness and suitability, system description, critical technical parameters. There's the integrated test program summary. So it talks about the test program schedule, management, participating organization, and includes the development, test, and evaluation, talking about the method of approach, the configurations that will be used, test objectives, events, and scenarios. There's the operational test and evaluation, which will include a discussion of purpose, configurations, test objectives, events, and schedules. There's also the test and evaluation resource summary. It includes a discussion about test articles, test sites, test instruments, test environments and sites, test support operations, computer simulations and models, and special requirements. There, in terms of specialty test equipment and test facilities, simulation of the system operational environment for the purpose of system test and evaluation can be a task of major proportions, sometimes approaching the magnitude of the system design and engineering effort itself. So we talked about facilities before, and so having an adequate test facility can be quite significant. If the advanced development phase, the aspects of system development is not only very important, but frequently is also very expensive. Thus, the judgment as to the degree of realism and precision that is required of such a simulation is an important system engineering function. Next, you want to be thinking about the creation of the test environment. The design and construction of the test environment to validate a major component or subsystem requires equipment for the realistic generation of all the input functions and the measurement of the resulting outputs. It also requires the prediction and generation of a set of outputs representing what the system element should produce if it operates according to its requirements. So you need to create that environment, what equipment, clearly define inputs and outputs, and all that is going to be put into a test plan that will be the focus of what will be done in the actual development test. So while I've been going through this, I've been showing this figure, and what this figure shows is a functional flow diagram. That it shows the four functions on the left side of the figure show how the design of the test environment creates a predictive test model and test scenario, which in turn activates a test stimulus generator. So we get a chance to be walking through some of these details as we're considering this. So the test stimuli activate the system element under test and are also used by the mathematical or physical model of the system elements to create a corresponding set of predicted outputs for comparison and with the actual test output. You need to have test software. And so one of the great things about test software is when you run it, it's actually going to be doing the same thing every time you run it. And so it helps to be rigorous in that you always have a good way of documenting that you did things in a certain way. Test support and analysis software requires special attention in virtually all developments and has to be tailored very specifically to the system at hand. Establishing of it as objectives and detailed requirements is a major system engineering task where users' interfaces are also involved. The task becomes even more complex. Well, one has to validate the test equipment before you can actually validate the hardware. And so it's going to be something similar. Like any system element, test equipment for system design validation itself requires test and validation to ensure that it's sufficiently accurate and reliable to serve as a measure of system performance. So you're measuring your development hardware, and so you don't want to have the test equipment be in the way, and so that's something that must be done. Then you actually are able to do the demonstration and validation testing, the actual conduct of tests to demonstrate and validate that the system design is often the most critical period in the development of a new system. The primary effort during advanced development has been seen to be concerned with the resolution and identification of design issues. In other words, eliminating the unknowns that might be lurking that haven't been figured out up to that point. Well, another thing that needs to be thought through and considered is what do you do if there is a test failure? And so is it a significant failure? And so did it uncover an unknown that folks were not aware of? All of those are things that need to be thought about. So the failure may be spectacular and publicly visible, or it may not. And because the failure is unexpected, there's a period of time before a proposed solution can be implemented. During this time, the impact of the failure on system development has to be considered and to adjudicate whether or not it is actually serious. So one way you don't want to have failures, but but on the flip side, you'd rather have it in the testing and you can go back and fix it rather than happen when it's in operation. There has to be consideration for testing and the system lifecycle. There may just be a one-time test that you do before it's goes forward to being approved and then put into operation. And so these are some things that you're hoping that the way that you're stressing it is going to point out anything that would get in the way for the whole life cycle. So a new system not only has to perform its operational environment, but also must be designed to survive conditions to which it will be exposed throughout its life cycle. So that includes shipping, storage, installation, and maintenance. These conditions are often things that may fall through the cracks, and you don't want to have that happen. Well, what about testing of design modification? The test programs must anticipate that unexpected results may occur and reveal design deficiencies. Accordingly, it must provide schedule, time, and resources to validate such changes that correct such deficiencies. And so is it the hardware? Is it something to do with the test equipment? All of those things need to be explored and then finally adjudicated. Then we have the analysis and evaluation of the test results. The outputs from the components or subsystem under test are either recorded for subsequent analysis or compared in real time with their predicted values from the simulated element model. The results must then be analyzed to disclose all significant discrepancies, to identify their source, and assess whether or not remedial measures are called for. So there's a lot of details that go on in the development testing. And then moving on, we have the evaluation of user interfaces. A special problem in the validation of system design is posted by the interface interactions between the user and the system. This is especially true in decision support systems where the system response is critically dependent on rapid and accurate information of complex information inputs by a human operator aided by displays driven by computer-based logic. So the test and evaluation of user interface controls and displays pose difficult problems because interfaces are inherently incapable of objective quantification, quantitative measurements, except in the most primitive features. So large variation in the experience, visual and logical skills, and personal likes and dislikes of individual users are things that start to pop up when you're doing this kind of evaluation. The evaluation of the user interface can be considered in 4 parts. 1, ease of learning to use the operational controls. 2, clarity of visual situational displays. 3, usefulness of information content to system operation. And 4, online user assistance. And finally, we want to be thinking about the correction of the design deficiencies. So all of the things that we've mentioned in this area centered on discovering potential deficiencies in a system design that may not have been eliminated in the development and test process. If the development has been generally successful, deficiencies that remain will prove hopefully to be relatively few, but how to eliminate them may not always be obvious or the effort required trivial. And so this is where another area that needs to be kicking up is how to then figure out what needs to be done. This is definitely a system engineering function that will be required to work through this process. And so there should be some kind of a board or mechanism to be presenting the results, presenting some recommendations and getting some approval to go forward. All right, this will be the last section that we will cover before our summary review, and this is dealing with risk reduction. A major fraction of risk reduction during the system lifecycle should be accomplished during the advanced development phase. To reiterate, the principal purpose of the advanced development phase is to reduce the potential risk in the development of a new complex system to a level where the functional design of all previously unproven subsystems and components has been validated. The typical sources of development risk are described in the functional analysis and design and prototype development areas that we have been talking about. Most of them are seen to arise because of a lack of adequate knowledge about new technologies, devices, or processes that are intended to be key elements in the system design. Thus, the process of risk reduction in this phase amounts to the acquisition of additional knowledge through analysis, simulation, or implementation and testing. We have advocated 2 primary methods to reduce risk within the phase: prototype development and development testing. While both methods could certainly be implemented earlier It is not until the advanced development phase that sufficient information on the system architecture is available to properly implement prototyping and advanced testing. Other risk reduction strategies are available to both the program manager and the system engineer. From the program manager's perspective, several acquisition strategies are available to reduce risk depending on the level of resources. One, parallel development of effort, developing alternative technologies or processes in case of a primary technology or process fails to mature. Two, alternative integration strategies to emphasize alternative interface conditions. And three, one of incremental development strategies to engineer functional increments while technologies mature. The system engineer also has several strategies available beyond those of prototyping and testing. One, increased use of modeling and simulation over physical prototyping to ensure increased understanding of the environment and system processes. And two, interface development and testing before engineered components are available to reduce interface risk. Regardless of strategies ultimately employed to reduce risk, the program manager and systems engineer work hand in hand to ensure risk reduction occurs at the proper time. What about how much development? A key decision that must be made in planning the risk reduction effort is by what means and how far should each risk area be developed. If the development is too limited, the residual risk will remain high. If it is very extensive, the time and cost consumed in risk reduction may necessarily inflate the total system development cost. Striking the proper balance calls on the exercise of expert systems engineering judgment. The decision as to how much development should be undertaken on a given component should be part of the risk management plan. The objective of the plan is to minimize the total cost of managing each significant risk area. The risk cost is the sum of the cost of such analysis, simulation, and design and testing that may be undertaken. That is the development cost and the cost of mitigating the residual risk to the low level required to proceed to the engineering design phase. That is the mitigation cost. By varying the nature and amount of development, a judgment can be made as to the most favorable balance. Thus, for a critical immature component, the balance may call for development up to the prototype stage, while for a non-critical or mature component, it would only call for an analysis. Okay, well, let's do our summary review and think about the things that we've covered in this chapter and in this lecture. First of all, reducing uncertainties. Objectives of the advanced development phase are to resolve the majority of uncertainties through analysis and development and validate the system design approach as a basis for full-scale engineering. The outputs of the advanced development are a system design specification, sometimes called a level B specification, and a validated development model. Advanced development is especially critical for a system containing extensive advanced development or unproven concepts that may involve several years of development effort. Activities encompassed by advanced development are requirements analysis, functional analysis and design, prototype development, test and evaluation. Then we talked about requirements analysis of system and functional specifications is required to relate them to their origin and operational requirements, especially those not readily met. Their difference from those of predecessor systems are also noted. Then we have functional analysis and design. Components that may require further development include the following: implement a new function, or a new implementation of an existing function, use a new production method of an existing type of component, extend the function of a proven component, involve complex functions, interfaces, and interactions. Then we had prototype development as a risk mitigation technique. Prototyping may be used for a variety of reasons. Some may be to reduce risk to the program, to explore technology limits, or inform the customer on cost and technical maturity. Program risks requiring development may result from a number of conditions: unusually high performance requirements, new materials and processes, extreme environmental conditions, complex component interfaces, and new software testing. In terms of development test, validation test to confirm resolution of risk requires the development of a formal test plan, as the TEMP, the test and evaluation master plan. Furthermore, test equipment must be developed, validated tests must be conducted, and test results analyzed and evaluated. The results of the testing lead to the correction of design deficiencies. However, special test equipment and facilities often represent a major investment. Therefore, early experimental exploration of interface designs is essential. Models of systems and components are used extensively in system development. Simulations are increasingly important in all stages of development and are essential to the analysis of dynamic systems and software that require development and a staff of analysts and operators. Development facilities are installations simulating environmental conditions and are used for development test and component evaluation. They represent a major investment and require a permanent operating staff. Finally, we talked about risk reduction. Risk assessment is a basic system engineering tool which is used throughout development, but especially during advanced development. It involves identifying sources of risk likelihood, and criticality. All right, well, thank you very much. That's going to end it for this chapter.